So thank you very much, Ravin. Is this working? Okay. Okay. So I'm deeply grateful to all the organizers for putting together such a wonderful gathering celebration on the occasion of TVR's 85th birthday, and also for giving me a chance to speak. Uh, Unfortunately, I'm not going to be here on Wednesday when the celebration takes place. So I would like to take a few minutes to say a few words about TVR here. Uh, in fact, this gives me an excuse to convey to TVR how much he has meant to me over the years and how his friendship and mentorship has enriched my life. You know, it's only at these occasions that we can say these things. That I cannot just walk up to somebody and say, "Hey, I really admire you." So this gives a good excuse. So we, of course, as Ravin said, we all know what a spectacular career TVR has had as a physicist. So his work on the scaling theory of localization, and I have, you can see two of the papers here, landmark papers there. It kind of transformed the way we think about transport in disordered media. When I began my career, this paper had just been published, and it was co-authored by Abrahams, Anderson, and Licciardello, and it was already recognized as a landmark paper, rapidly making its way into textbooks, which is what we all dream of. The paper was so influential that the authors were given the nickname Gang of Four, okay, because of the influence this paper had. But I should say that for many Indians, it was a matter of tremendous pride, and it gave us a real life proof of principle that and confidence that Indians can also contribute to deepest questions in physics. TVR, you probably don't remember when we first met. So this was Rajiv Singh and I came to Princeton to see you once when we were both students at Stony Brook. So I was kind of nervous, you know, because TVR had a larger than life persona and his reputation, of course, always preceded him. So I didn't know, I was unsure as to what would happen, but you know, in hindsight, I did not need to be worried. I mean, over the years, as I have got to know TVR personally, I discovered that he's as good and decent a human being as he is a physicist. So we have met at many places. So once it was at Oxford, and TVR told me, look, there is a lecture by Amartya Sen, and the title of the lecture was The Argumentative Indian, I believe. And so we went to that lecture together, and TVR made a remark after that lecture, which I thought was, I was kind of surprised by that remark, but I'm not going to repeat that. And later, we met pretty regularly at IISc, where I was visiting very often as an Infosys professor. And during one of those visits, TVR and Meeraji, he's not here. So they were very gracious to invite me to their home for a very delicious dinner. And the photograph you see, so they invited me and Manju, my wife. Manju is taking the photograph, so she doesn't show up in this. These were times before selfies were invented. So one of the things that I learned about TVR is that he does not just make time to see young Indian scientists, but he actually keeps track of what they do, where they are, what their career trajectories are. Um, I mean, he genuinely cares about Indian physics. I recall I was quite surprised once that he had not only remembered what I had done, some work that I was doing, but he even followed up on it. So it kind of made me feel that he really cares. And I know by now that behind the scenes he works very hard to nominate people for prizes, to make sure that people get whatever credit they deserve. So when I was coming from New York to Delhi on my long flight, I took a look at my email, all the email exchanges I have had with TVR, and there's a long list of emails. Some emails were congratulatory. In some, he said, he offered me valuable career advice. In fact, one email, he offered me advice on how I should respond to someone named Keshav and Srivastava, who wanted to come and visit me and also see me at the March meeting. Many emails were, so whenever I come to India, I make it a point to see TVR. So many emails were just trying to figure out where and when we can meet. Then there was this, you might remember, quantum condensed metaphysics proposal that Arindam and Vijay Shenoy and you and I had kind of, Arindam, yeah. So we had worked on that. And then we also worked on another proposal, which was an attempt to try to assimilate Indian physicists abroad in a way that could be mutually beneficial. We called it Vigyan. Okay, so that's a virtual, globally integrative academic network. Didn't get anywhere, but so when I was sifting through these emails, I was kind of struck by the fact that how many times I had bothered TVR for advice on personal things, but that's just a sign of the fact that I thought I was very close to him. But TVR always did respond, and his responses were always very thoughtful. So let me just say that you have been kind of a constant and reassuring presence, nurturing young scientists, inspiring them to do well. And I guess there's one more thing I would like to add, which is that often the culture of a scientific community is decided by the senior people working in the field. So TVR nurtured a community that does not tear itself apart. So it's a community where people support one another. They take pleasure in others' successes. So happy 85th birthday, TVR. It's been an honor and pleasure to have known you. So my talk today, I have changed the title, given that this is the part of work that matches more nicely with TVR's contributions. So the title is Scaling in Fractal Quantum Hall Effect, a recent progress on a long-standing problem. And what I'm going to tell you is not the real progress. The real progress will be the experimental work on this by Avik Brit, who has done a beautiful experiment on this. So the plan, to the extent Ravin would let me finish this talk, I will first say some quick words about scaling in integer quantum Hall effect. I will then give a very quick introduction to composite fermions and talk about a law of corresponding states, which implies, if true, this law would imply universal scaling. So same scaling behavior in integer and fractal Hall effects. I will then provide some theoretical evidence for the law of corresponding states. And then the experiment on that was done by Avik would be the matter of the next talk. And if time permits, I will give you a review, a quick lightning overview of other developments and miscellaneous remarks. Okay, so this gang of four paper made the assertion that for non-interacting electrons in 2 dimensions, there is no matter. So any small amount of disorder localizes all states. That was a very dramatic assertion. But when integer quantum Hall effect was discovered, this was a 2-dimensional system, and this system has 0 resistance. So the question was, how can we have 0 resistance? So because of field theory and many other works, it was that the picture that finally we had was that there is one energy in each lambda level. So these are lambda levels, they're broadened because of disorder. But there is one energy at which we have extended states. Okay, so in the presence of magnetic field, extended states are possible. Moreover, as you approach the extended states, the localization length diverges with an exponent, which is called gamma here. How do we measure this exponent? Well, one can, so if let's say the, okay, if the localization length is, in the ideal limit, when the sample is infinitely large and the temperature is 0, one would go from one plateau to the next in a jump. But because of finite system size and so on, it's the jump is smoothened to a certain extent. So one can look at the width of the peak of the longitudinal resistance and ask how that goes to 0. So this is the width of the peak delta. It goes to 0 as a function of temperature with an exponent kappa, which is related to gamma and the dynamical exponent. So numerical studies showed that gamma is equal to 2.3. And if we take dynamical exponent to be 1, we expect that the width of the RXX peaks goes to 0 with an exponent which is 0.41. So it took some time to understand where this exponent is to be measured or where we reach the critical regime. But once it was known, Dan Sui and his group showed that the exponent is extremely well defined over at least 2 decades, and it's equal to 0.42. So it agrees quite well with the theoretical prediction. In fact, Dan Sui used to say that this is the most convincing and perhaps the only real proof of scaling in 2 dimensions. So the question is, how about the plateau transitions in the fractal quantum Hall effect? Now, this is an interesting problem because here the interaction between electrons plays a non-perturbative role, as does disorder. So the problem seems at first rather complicated, and it's not really clear how to go about it. So let me, because it will be through composite fermions that we will try to understand this, let me introduce them very quickly. So the problem that we want to solve is that of 2-dimensional electrons in the lowest lambda level, whose Hamiltonian is given by, as shown here. So I have not included disorder as yet. Notice that there are no parameters in this problem. So of course, Coulomb interaction has E squared and R and so on, but all of these parameters can be absorbed into the units. There is no mass. The electron mass is not a parameter because here I have taken the limit where the cyclotron energy is very large compared to interaction. So all electrons are within the lowest Lambda level, and there is no kinetic energy in this problem, only interaction energy. So this is the problem we would like to solve as a function of the filling factor to understand the phenomenon of the fractal quantum Hall effect. So at first, it might seem that this is an impossible problem to solve for the following reasons. It's of course, so now we talk about flat bands, it's become like a common terminology, but this is a flat band. So there is no kinetic energy. The kinetic energy is just constant. This is the most strongly correlated system in the world because the ratio of the interaction to kinetic energy is equal to infinity because there is no kinetic energy. It turns out there is no exact solution to this problem, but of course that never deters condensed matter phases because if we only cared about exact solutions, we could as well go home. We always, we know that one can use approximations and obtain an extremely good understanding of many systems that contain an Avogadro number of particles. But typically when we want to make approximations, we need a small parameter, but there is no small parameter here to guide us. We cannot do any perturbation theory for this problem. And if you just switch off the interaction for a moment, ask what we are dealing with, you realize that it has exponentially large number of degenerate ground states in the absence of interaction. And of course, interaction now takes these states and it mixes and matches them or entangles them in some very beautiful way to produce this phenomenology that we see. So the question is, what is interaction doing? But not even knowing where to begin, how are we ever going to figure out what's happening? Well, it turns out that this, in spite of all this, this is one of the best understood, strongly correlated, I would say the best understood, strongly correlated system. And the theory for this, the statement of the theory can be summarized on a single slide. So I won't have time to go into the motivation that led to this or the unfolding of the experimental phenomenology that led to composite fermions, but the statement is as follows. In the presence of a strong magnetic field, electrons, to minimize the energy, capture 2 or 4 or 6 flux quanta of the external magnetic field to turn into these new particles, which are called composite fermions. The key property of composite fermions is that they no longer see the flux that they have captured. So the magnetic field they see is called B star. It's equal to the external field minus the captured flux. And now we just boldly go ahead and we say we'll treat composite fermions just as ordinary non-interacting fermions in this reduced magnetic field. So they have a filling factor nu star. Electron filling factor nu is given by this equation. So the basic premise, the central claim of composite fermion theory is that we can take this very strongly correlated system and look at it as a weakly interacting system of composite fermions at an effective magnetic field. Now, once you know just this is good enough for lots and lots of experimental results. Experimentalists, this is all they need to know. But one can also, once we know the connection between B and B star or nu and nu star, we can try to construct ansatz wave functions. So I take wave functions of non-interacting electrons at nu star and composite fermionize all electrons by multiplication by this Jastrow factor, which attaches 2m vortices or 2m flux quanta. This is to be followed by projection into the lowest lambda level, and that we declare to be the wave function of strongly interacting electrons at filling factor nu. So it turns out that the integer quantum Hall effect of composite fermions, where they fill p lambda-like levels, corresponds to fractional Hall effect of electrons at these filling factors. And these are most of the filling factors which are observed. As you can see here, in fact, this and this, they are the same figures, except that this is plotted as a function of B star. And you can see that the fractions 1/3, 2/5, 3/7, etc., they all align with 1, 2, 3, 4. So you can see a correspondence between the fractional and the integer Hall effect here. Okay, so in 1990, Nandini, who is here, and Steve Kivelston and I said that if there is a correspondence between the integer and fractional Hall effect, and if this correspondence holds even in the presence of disorder, then what does that mean? That means that, let's say, if I can calculate the ground state for non-interacting particles at filling factor nu star, and I can calculate the ground state of interacting particles at filling factor nu, then these two ground states are related by this formula that I had showed earlier on the previous slide. So by composite fermionizing the problem at integer filling or for non-interacting particles at nu star, I get the ground state at filling factor nu. So if this is true, then the fractional and the integer Hall states would have the same exponents. Plateau transition would be decided, would correspond to the same exponent. The exponent is universal. We also said that we can also predict where the transition or where the jump from one plateau to another would occur. So if in integer, it occurs halfway between two integers, then for fractions, it would occur at formulas given by this expression. Now, since 1990, we have made a lot of progress in learning how to calculate quantitatively with composite fermion theory. So we thought we would revisit this issue. Let me just first tell you how the law of corresponding states works without disorder. And then we'll see how to include disorder. So for filling factor, there is a correspondence between the ground states at filling factor 1 and 1/3, 2 and 2/5, 3 and 3/7, and microscopically it's kind of encapsulated in these equations here. Similarly, we would say excitations, a quasi-particle is nothing but a composite fermion that's excited to a higher lambda level like this. So these are lambda levels of composite fermions. Everything is happening within the lowest electronic lambda level. So just this isolated composite fermion is a quasi-particle. A missing composite fermion is a quasi-hole. And neutral excitations are excitons of composite fermions as given here. So they are particle-hole pairs of composite fermions. Let's see how well the correspondence works. So here, I'm taking an example. It's filling factor 3/7. We have 18 electrons. This is the exact spectrum. So we take 18 electrons, put it, I mean, the geometry used here is the spherical geometry. So electrons are moving on the surface of the sphere, subject to a radial magnetic field, which gives us filling factor 3.7. So 18 particles is not a small system, it's a fairly big system. These are exact eigenstates. And what I have done, so because of the geometry, they're labeled by the orbital angular momentum, because spherical geometry. On top is the number of basis functions for any given angular momentum. So you can see for, number of basis functions is like a few million or more. So any given state here is a linear superposition of a few million basis functions. So to define a state here, I have to give you a few million numbers. Okay, it's projections of this eigenstate in all directions of the Hilbert space. And you can see there are some gaps opening. All of this is happening because of Coulomb interaction. If I switch off the Coulomb interaction, they all collapse into a single energy. So this is like non-perturbative physics here. What does composite fermion theory say? Well, it would say that this ought to be interpreted as three filled levels of composite fermions. These are neutral excitations. It's a particle-hole pair. It turns out these wave functions have no adjustable parameters, okay? And neither do these. So we take these wave functions, we calculate their energies, and we get these dots. Extremely good accuracy. So in fact, initially, so when I first wrote these wave functions, I never thought they would be quantitatively accurate. And we were kind of blown away when we first found how good they were. And still, like Senthil was asking me last time we met, why are the wave functions so good? I said, I don't know, but I will take it. But it, you could now say, how about these guys? So these are excitations which have two kinetic energies. And in fact, we can understand those in terms of these guys. We go to three kinetic energy excitations, we'll capture all of these. So we can fill, in successively higher and higher energy states in a systematic way. There's nothing special about, 3/7. This is true at all filling factors, this picture I showed, or in between these special filling factors. So here we have 4 quasiparticles or 6. Again, the composite fermion theory gives a good description of the low energy states. This is 1/3, for example, 2/5. Okay, so you could, I like to give this analogy. Let's look at the problem from a different perspective. Let's say I know how to do exact diagonalization. I calculate all eigenstates and, list them. So I'll have reams and reams of numbers. So the computer gives me the solution, but it doesn't tell me how to think about it. Okay, so it doesn't tell me what these numbers mean. But we can throw away all of those numbers, and we can just synthesize all of them into this equation. Because if you unpack this equation, you'll get those numbers, extremely good approximations of those numbers. And this equation also tells us what the physics is, because here we have nu star, and this tells us that electrons have vortices bound to them. So you interpret that as a new particle, and that's the composite fermion physics. Okay. So now coming back to our problem, let's look at how a single quasi-particle or quasi-hole is going. So this is a single quasi-hole. There are 2 curves here. One is exact density profile. The other is density profile computed with this. And you can see there is extremely good agreement. Again, this is for 2/5, 3/7. You may not even realize that there are two curves here. 5 minutes. Okay. So you may say there is some sort of paradox here. So I just told you that a quasi-particle is just an excited composite fermion. Composite fermion is charge E bound to vortices, so you may say it's a fermion. But aren't the quasi-particles actually charged anions? Well, there is no contradiction really, because it turns out if you ask what is the excess charge, okay, so you say when I add a composite fermion, I add two flux quanta or two vortices and an electron, a vortex, if you do it adiabatically, has a charge equal to the filling factor. So 2m vortices have charge this much. This is the charge of an electron. You add this up, you get a fractional excess of the charge. And similarly, you can show that they behave as anions in the sense that if you ask what is the fractional or what is the excess flux associated with this, that would be also a fractional number. So we have these objects which are fractionally charged anions. Okay. Now the correspondence in the presence of disorder. So that's the question that I had raised earlier. So this work was done by Songyang Koo and Sridit a few years ago. And let's now introduce disorder, and I'll go somewhat more quickly over this. So let's assume disorder is something like some delta function scattered all over. There is some on-site energy, and let's assume that it's weak enough that it only binds the quasi-particle, but it does not distort the wave function of the quasi-particle. So then the question is, let's say I have these disordered potential and I leave a single composite, a single quasi-particle. What is the localization length of the quasi-particle? So what we are going to do is, we are going to take a basis which is the quasi-particle at different positions of the disorder, and we will basically work with a model where it's like a hopping model to figure out what the wave function is. These different basis functions are not orthogonal, so we need to diagonalize O inverse H, where O is the overlap matrix and H is the Hamiltonian matrix. In the interest of time, let me just say that we can, that numerical calculations, so on the one hand, we do full many-body theory to figure out what's the overlap between the quasi-particle here and quasi-particle here, or the matrix element of the interaction. On the other hand, we go to the effective magnetic field and we do a single particle calculation, and we find that they agree extremely well. So here are some, okay, I won't have time to explain what these are, but the symbols here are the full many-body calculations, and the lines or curves are analytical results at the corresponding non-interacting problem. So if given that both H and O have the same matrix, it then follows that there is correspondence between the eigenfunctions of those. And let me just, so this says that if you let's say start at filling factor, let's say 3/7 and leave a single quasi-particle at different energies, this would have the same behavior as an electron would in the 4th Landau level of the non-interacting problem. What about many quasi-particles? So experimentally, as we'll see, the experiment changes the filling factor. So here we say that if the wave function of the quasi-particle is sufficiently extended that it averages things out, then the effective magnetic field can be replaced by its average value, and again the whole thing goes through. Okay, so we therefore conclude that the exponent for the fractal Hall ought to be the same, ought to be equal to the exponent for the integer quantum Hall effect. Okay, so I think this is the experiment. That is the next talk, and maybe this is a good point to stop. Thank you. Thank you all very much.
We're open for questions. Maybe I'll start the questioning. Yes. So, of course, this, as we are very convincingly shown, the composite fermion theory works amazingly. But perhaps you can tell us a little bit about which fraction this is and whether you have any thoughts about it.
Okay, so so there are three different mechanisms for fractal Hall effect. Integer quantum Hall effect or composite fermions is one mechanism. It captures maybe 80–85% of all the fractions. Another mechanism is pairing of composite fermions. So that arises when you include interactions between composite fermions, and the interactions are weak, but sometimes they can be weakly attractive. So there are many even denominator fractions that have been observed, like 5/2, 1/2, 1/4. Third mechanism is fractional quantum Hall effect of composite fermions, which also occurs because of the weak residual interaction between composite fermions. So that gives fractions like 4/11, 5/13, and I think these capture all the fractions. Although if Ajit was here, he would always say, no, there is one fraction which is not explained, but it basically captures all the fractions. Yeah.
So the calculation is done from the experiment verified this
Yeah. I agree with you. So I think to my understanding, even for the integer Hall problem, it's not completely well understood. And one often uses language where you sometimes assume they're not interacting, but when you say the dynamical exponent is 1, you're thinking of Coulomb interaction, so sometimes you say you can, in fact, composite fermion quasiparticles are they are more non-interacting than electrons are, because their charge is E star, which can be 1/3 or 1/5, so it decreases the interaction by a factor of 1/9 at least. But I agree with you that in principle, it's something that needs better understanding. Yeah. So I do not say anything about integer. I just say whatever is happening for integers, same thing should happen for fraction. Yes, dear.
Thank you for a wonderful talk. Of course, wave functions are wonderful for condensed matter physics, but we know of many things, such as the way you're looking at me now is via light, which we describe using field theory. So what's the field theory of all of this? You didn't discuss that. Is it Chern-Simons theory, or is it something more than that?
Yeah. Some people think that there's something more, as you know, like Damson has found that the Chern-Simons theory does not satisfy exact particle-hole symmetry at filling factor 1/2. So I think, okay, so there is no field theory which gives numbers. So in Chern-Simons field theory, you need kinetic energy plus interaction energy. You need kinetic energy in order to be able to make this singular gauge transformation. And so you have an electron mass, and if you just uh, honestly proceed, you cannot get rid of the electron mass. Maybe, Senthil, you might tell me if I'm saying something wrong. But I think what people do is they replace electron mass by m star and interpret it as mass of the composite fermion, which is not completely satisfactory. Until you.
Yeah, but for the real, but only this in fact,
Topological properties. Okay, for topological properties, all these theories are good.
But maybe
the
there's scope for
numbers-
further developments.
Yeah.
Yeah.
So I mean, the problem here is that there is no small parameter in it. So that I guess hinders calculation of actual number.
Good talk. Actually, I have couple of questions. In the slide number 2, you were discussing about the relation between kappa and gamma z, and you have taken z equal to 1. So what is the reason behind only taking 1? You can take a fractional value also.
Yeah. So it's okay. There are experts in the audience who are much better equipped to answer that question, but Coulomb interaction has dynamical exponent 1, but maybe is there a deeper? Why can it not be something else?
Coulomb, long range is that the long range phenomenon.
Yeah,
So that's all.
you understand?
There could be a difference. They become diffusive. Then, the dynamical exponent could change. It's